Hi, good afternoon. Welcome to this presentation in AI for Artificial Intelligence for Agriculture, Automated Vigor Estimation on Vineyards. And this is a work by Maria Pantoja, myself, Andrés Honeyman, and David Guerrero. It's actually a collaboration between two universities, CalPoly in California, USA, and INACAP in Santiago de Chile. Okay, so first I'm going to talk about an introduction to the topic, and then implementation, and talk about the implementation and summarize the results. Okay, so the estimation of vigor or the balance on a vineyard is actually very important for the farmers because it gives them an estimation of the yield, the production that they are going to have during the harvest, of course, and allows them to prepare for it. For many years, hundreds of years, this vigor has been estimated during the dormant state, and the dormant state is when the plant, the grapevine, doesn't have any leaves still, so that's called the dormant state. So all you can see is basically the canes for the vine tree. And so the traditionally, what the farmers do to estimate the vigor is that during this dormant state, they actually have to prune the vine trees anyway, so they prune the vines and they weight the canes for the specific plant. And then they do the same during the harvest. They weight the grapes for that same tree, and they divide the weight of the canes by the weight of the harvest, and that's what is called the vigor. So as you can see, it's actually a very manual work. You have to one by one go through the vine tree and prune it and individually weight the tree, and then do the same during the harvest. So it's very manual, and because it requires it's extra work that the farmers need to do, so it's expensive, and because of that, what generally the farmers are going to do is just get the weight of a couple of trees on the entire orchard, and with that they estimate the same yield for the entire orchard. And by that, we lose a lot of the precision, the variability that you have in the terrain, and the difference, for example, in the slope and so on for the terrain, or the kind of ground and so on, that actually changes the yield of the plant. And we, by doing a general average, we actually lose these specific values that will allow the farmer also to target a specific improvements. So to avoid this, having to do a general average of the entire orchard, what we want is to decrease the labor for estimating the vigor. And we want to automatize it, and we also wanted to do it with technology that already farmers do have. So they don't have to buy some expensive equipment like a drone or anything like that. So the idea is to, with a cellular phone, that the smartphones that most of us already have, to go to the orchard and take a picture of the vine, and then with computer vision techniques, evaluate, segment the image and get an estimation of the weight of the cane without even having to cut the canes or anything like that. And in this, you take the picture and the picture gets evaluated and directly writes the results into a Excel spreadsheet. And then with that Excel spreadsheet, you can actually create that's the input to the software that creates the precision maps, like the one you have on the figure, that shows the different areas of the orchard that has a lot of vigor, like the red, or lower vigor, like the yellow areas. And then the farmer can adapt the techniques that they are using. For example, add more fertilizer or decrease the amount of fertilizer in the specific areas, because what you want is to have a balanced orchard. So all the vines to give not too much, not too little, the perfect amount, and all of them the same. And again, our idea is to automatize this process. To give you an idea of what the problem is from the computer science point of view, is like when you actually take a picture of the vine on the field, lighting conditions some days are very light, sometimes it's raining, right? But the biggest problem that we have is not so much the light. The biggest problem that we have is that the lines of on the orchard are actually very close, so within 1 meter, 1.5 meters, and that makes the background very busy. So it's even for a human, it's actually very difficult to see which canes belong to the front vine as opposed to the one that is right behind it. So it's a segmentation problem, right? To make the segmentation problem easier, then the first approach we did is then to put an artificial background. So when we take the picture, get also somebody that behind the tree, gets behind the tree, put a white background, like for a photographic studio. And with that, it's very easy to subtract the background. And you can see the image with the artificial background, how accurate the segmentation algorithm is. So it's very precise, right? With an artificial background. But because the main purpose of the work was actually to decrease the amount of work, manual labor that it takes the farmers to calculate this vigor, then we actually wanted to get rid of the background. So once we have a solution, we wanted to improve it and make it so it doesn't need the background. And because we were using the cellular phones and the smartphones, current smartphones, most of them, they already have 2 cameras on the back. And therefore they can actually create depths. And we wanted to use, because we get a depth estimation already with the camera, we wanted to use that depth estimation to actually be able to to subtract the background without having to have that artificial background. And in this slide, just a reminder of physics from when we went to high school or the early years of the university, that the reason why we need a cellular phone with more than 1 camera is because the moment that you have 2 cameras, then you can actually create that disparity. So you can measure distance to objects. That's called the disparity. And therefore create the depth maps that then we are going to use on our algorithms to refine and get a better segmentation. The thing is that the depth map is not good enough. It just misses a lot of the small canes that are in there that actually also belong to the tree. So to improve the algorithm, we decided to use as a solution to add the alpha mate segmentation, which is with deep learning. And so alpha mate segmentation is basically a segmentation that is very fine, very refined. So that's a segmentation that, for example, is a segmentation of me. Then if my hair see, it doesn't do it, right? That's something. But if my hair is a little bit all over the place, then the segmentation will actually go through each one of my individual hairs, because we really need the accuracy. So that's the alpha mate. And then the latest solution to the alpha mate segmentation has been deep learning, using deep learning. And what they use is, so we were reusing the deep learning solution that is already out there, the alpha deep mate solution, which requires the original image and what they call a trimap. And a trimap is an image that only contains pixels that are foreground, background, in the frontier. So let me go back a little bit, one slide. So I went forward. So what we were trying to do is to be able to use that deep alpha mate, we were actually, we needed to create this trimap. And what we did is create automatically the trimaps from the depth map. Because actually trimap, the problem with alpha mate is that getting the images that are already so finely segmented is actually very time consuming also. So we were using the depth map to create the alpha mate trimap, and then we feed the original image and the trimap to the deep mate. And these are the steps of the algorithm, and I'm running a little bit out of time. So here are the steps, and the last one is like, once we have the trimap, we actually run it through the algorithm, and then we are able to just segment the image. And because it's as difficult, the mate of a vine is basically as difficult as the hair of a human, right? So that's why we wanted the accuracy. This is actually the deep alpha mate. So it's a segmentation algorithm. So it still has that U-shape that you do decrease and you do max poly, and then increase the size. So it's basically a U-net, but segmentation, but it does also get the input, the alpha mate, the original image, and the alpha mate. So when it creates the output, it's creating, the output is not so much this image, is actually the segmentation with full accuracy, right? Because it runs on the frontiers only. So it runs a refine on the frontiers. This is the last step, which is the refinement. This is a paper that describes the alpha mate that we use. So if you want to know more, there's a link. And the results, so once we actually run the algorithm, we want to create those precision agriculture maps, right? So we want to compare if the precision agriculture maps that we are getting with and without background, they have to be equivalent to be able to say, okay, so go ahead and take the picture without the background, and then we will directly create the image. And that's, so I have more results, I have more, but they all look like this. So it's maps of different orchards that we actually took the picture of. And this one here is the map of the, that we generate when we actually use the artificial background. And this is the same, but without the artificial background. So as you can see, the areas of higher yield compared to the lower yield are actually very similar, are actually basically equivalent from the point of view of the farmer. They are the same. And that's it, that's the presentation. I have my email on the article that I submitted. So if you have any question, I'm more than happy to answer them. Don't hesitate to send the email. Thank you so much. Hope I see you in person next year. Bye.